Okay, so let me show you something here. On the syllabus, and you have the TA office hours, and you can find out your TA here at the room South Hall 4519 on Wednesday 9 a.m. to 10 a.m. And also you have another office hours on Thursday. Is from 5 to 7 on the first floor of the South Hall. And you can ask any homework questions and lecture questions in both office hours. And so his name is Angie, and I haven't met him in person, so I don't know what he looks like. So you can just say, you can go to his office hours first, this one, and then you would meet acquaintance of him, and then you could go to the MATLAB hours later, or you can just go inside the MATLAB hours and then, hi, where's Angie? And that's the way to find out your TA. And so also we got the assignments here, the first assignment, and I'm changing the way of the submissions. We have the homework one here, and then the due time is still on, let me see, it's January 18th, that is this Thursday in the evening, 11 p.m. And you can just submit your homeworks on the cameras, and you need to generate. You need to scan your work and then transform it to the PDF and then submit it here. And I'm going to give up the Grayscale this time because the Canvas is more integrated. So this is some things I want to let you know before the class. And the next things is go back to what we have from the last time. So I got several very good questions. Let me see. Let me just, okay. I get a couple of good questions in the last class, and so let me share the screen here. Okay. So let us take a look what we have from the last time. We have this. So last time I just have the cancellations error, and then one of the students is asking, is there any cancellations in the cancellations error? If I remember it right, and then the cancellation error. So I mentioned this last time. The error for the x plus y, if we use the rounding off for the x and then rounding off for the y, and then the error for the addition, it should be x and then delta x. That is the errors in the x terms, and then y, delta y, and then at the bottom it should be x plus y. And I think that the error would be very large, and then if the x plus y is close to 0, right? And then one of the students is asking, is there any cancellations in the numerator and denominator? Because in her point of view, and then if we have delta x and delta y is the same, and then we have x plus y, and then maybe delta and then x plus y here. But and then we can have the cancellation, and then we don't have the magnifications phenomenon here. But for this one, you could see it requires the delta is almost the same. So I have one example here for the cancellations error, and then which would magnify by this diameter. So I have this example after the class, and then I have the x here. I have the x here, and then I have, so here I have only I only keep 4 digits after the decimal points. And here I also have 4 digits, right? I am missing, this one missing. If I want to keep just 3 decimal points in the rounding off, and then what would happen? So the rounding, the approximations of the x is the 0.999, because this one is below, the 4 here is below 5. So I just take 0.999. And then for the y, the approximation should be, and then this one should be 0.000. And then now I'm doing the subtractions here. And then for the real one, this is the exact value. Y minus x is the 0.0007. But if I use the approximations value, what can I get? It is the 0.001. So I write one more 0 here so that we can do the subtractions here. Error. But actually we have only 3 digits, 3 decimal digits. And then now, so we do the subtractions here. And then actually in the computer, we are using the, oh, I'm answering your questions. Hey, I'm answering your questions here. Are you? No, another girl, sorry. I missed you guys here, sorry. And let's go back to this example. So let's get the error for the y minus x. So we are using this approximations value to approximate y minus x. And although it seems that it is really close to each other, but we are calculating the relative error. The relative error here, it should be, this is the rounding error, this is approximation error, approximation value, and then this one is the exact value. So we use the approximation value to minus the exact value, and then we get the approximation error, and then divided by the exact value, and then we get the relative error. So now, what is the relative error in the subtractions? The relative error in the subtractions, we got almost 42%, 43%, almost 50%, right? And that is really big. But if we go back to take a look what errors we have in the x and y, we do the relative error again, and then you will see the error in x and error in y is really small. And then you will see this is 0.04%, and then this is 0.01%. So now you will see the magnification here by this one, x plus y. You see it magnifies to like 10 to the power of 4, right? So this is one example in the cancellation error, which is magnified by the denominator x plus y. And this is one example. Also, I have 2 pictures here to show you the intuitive intuitions of the backward difference and then center difference formula. And I remember that we haven't finished the derivations of the center difference formula yet. So let's go back to the center difference formulas, the derivations. So let me see. I should erase this. Never mind. And then so last time I also in the appendix for the lectures, I show you the this is the Newton's form for the approximations, and it's in the chapter 3, section 3.4 in the textbook, and then this is mentioned in the Math 104A. And I just briefly record this in this lecture, and we are using the polynomials the n degree, the polynomial with degree n to approximate the function f. And for the function f, we already have the formula for the, maybe we don't have the formula for the f. We just have some data points, and then we want to approximate the f functions. And this is how we approximate the f functions with the data points we have, and with the Newton's format. We have the Pnx, and then this is f x0, fx0, x1, fx0, x1, x2, and then to this one. And then are the divided differential as below these tables. These are the coefficients here, and then these are the polynomial here, the polynomials after the coefficients. And we use this sum as the polynomials with degree n to approximate the function f. And this finite difference, this is not finite difference, this is the divided difference table to get the coefficients here. So how does it look like, this divided difference table? So first, on the intervals, so we are using, so this is some of things we learned in the Math 104A. And then in case that you forget all the materials you learned in the last semester, so I'm just doing some brief review on it. And then, so this is some points on the interval. And then we are using the Pn to approximating the f functions here. And the Newton's force or the Lagrange force has one benefit, and that's we have the nodal points here, right? And then if you get, for example, we are getting the n degree, and then if n degree of the n degree polynomial, and then it would, this is the approximation, maybe this is the approximations of the f function, and then you will see this n degree polynomials, it agrees, this is a Pnx, and then it's using the Pnx to approximate the fx, and then this, we have some benefits of the Pnx. The Pnxi agrees with the f functions evaluated at the xi for all the I in between 0, 1. So that is all the nodal points. It agrees the values on the nodal points. And so now we have the nodal points, and then we also get the values evaluated at f, and then we use the square bracket here. And then the first divided difference is calculated in this way. We use the below 1 to minus the above 1, and then divided by the this columns x1 minus x0. And this is the first divided difference. And then you will see the similar things for the fx1, fx2, and then we get the middle values, the middle formula here. And then this is the first divided difference of this two. And then we use this one minus this one, and then divided by this one minus this one. And for the second divided difference, we can do the similar things. We use these things. So here we use these things, this minus this, and then divided. So divided, if you go back, and then you will see is the x2 and x0. So we, in the denominator, we have x2 minus x0. And for, this is a second divided difference. And then for the third divided difference, we are using the same way. We are using these things minus these things, and then go all the way back. And then you will see we only involve, or you can just see the minimum point here, x0, and then this is the maximum point here, x3, and then we use the x3 minus x0. This is the third divided difference. Do you remember this? Yes, okay. So this is all the things we have learned in the Math 104A. So now let us use this format to generate. So here we are going to, we are not using so many points. We have n plus 1 points here. But today, we are going to use this. And today, we are going to use only 3 points here to generate the polynomials we want. We have 2 degrees. Not 2. Let me see. Am I right here? I think. Let me see. Okay. So we have x0 here, and then we have one more point. Is x1, x2. x2 is the x0 plus h. It's the step size, and then the x1 is the x0 minus h. And the center difference should be, and we have. Let me see. I think I have mixed some error here. It should be. So this one, it should be. This one, it should be 2. So I'm changing some indexings here. This is x1, x0, x2. Usually in the divided difference table, you have x0, x1, x2, right? So I'm switching some point here, but it doesn't matter the index. So here from the divided difference tables and the Newton's formulas, and then we have this formulas, and this is by using the Newton's form, and then we have fx1, and then that is the first point here, and then fx1 x0 minus x1. Let me see, it's true, yeah, and then plus these things. And so after some while, and then we have the divided difference table here, and then remember that we are changing the x1 to here, and now we are calculating the difference here. Now I got the formulas, and I got the values for the fx1, that is this coefficients, and then I got the coefficients here, the second coefficients, and then I got the third coefficients here. And now what should I do with all these things? I can go back to plot in the values to this P2 function, and again I got the approximations for the f functions. But I am approximating to the f functions. What I'm going to get is, don't forget what we are going to investigate. We want to get the different formulas to approximate the f prime x. And then now what we get is the P2x. And then the P2x is approximating the fx. So if we want to get the approximations for the f function, then we need to take the P2 prime x. That is taking the derivative of the P2. And so if we take the derivative of the P2, and then we get, so for the first term, we just remove all the things, and then we got the this one. If you take the derivative, first derivative, this becomes 0. And then for this one, if you take the first derivative, and then we got fx1, x0, and then that is the number here. And then so the first derivative of the P2, we have 1 term here, and then that is these things. And then the second term, so if you take the derivative of this one, and then if you get the first derivative, and then evaluate at the x0, because we are approximating the functions f prime, and then on the derivative of the f prime, the derivative of the f evaluate at x0. So we need to do the plotting after we get the derivative of here, and then we got the things. It looks like this. we have this one keep us the constant. So we have such a term here. So this term is corresponding to this term here. So you will see such a term here. And then if you get the first derivative of the x minus x1, x minus x2, and then you would get the, I think here is still x0. It's still x0. I make the mixer here because actually I changed the index. So it should be the second point here in the parentheses. So if we take the derivative and then you would use the product rule and then you do the substitutions, x equals to x0, and then we got the h here. And then after some cancellations, you will see, okay, after some cancellations, you will see we got this is not the difference formulas we want. This is, what we want here is the center difference formula. The center difference formula. And it should be, this is the center difference formula. Let me see. And the center difference formula, it should be this. And it's this one. Let me see. Yes, it is. And this is the center difference formulas at the end. You would do some cancellations here, and then let's calculate it. And so for the first one, we have P2 point x, and then we have equals to fx0, and then minus the fx0 minus xy. And then this is the derivative, the first term, the second term, then the derivative of the second term. And then there, derivative of the third term, we have this, right? And don't forget that we have doing some cancellation here in the denominator and the numerator. And we got 2h because we have the cancellation here in the numerator and denominator. So now you also have some cancellations in the numerator as well. So let's get the common denominator here. We have 2, we have 2 here, we have 2 here. And then now if you do the sum of the numerator, and then you would get this. We cancel out the 2 at x0 there. So we got this. This is the center difference formula. And once again, you have the approximations error. And then this approximation error is already shown in the previous class. We have one formula for the difference. So this one is the error when we do the approximation. And then I have briefly mentioned this in the last class. And then if we take the derivative and then the derivative of this one, and then the derivative of this one, and then it would be the error in the approximations of the differentiations. And then the error term is here. So now let's just do some plugging here. N equals to 2. So we have 1/3 factorial here, and then we got other terms, and then it should be this. At the end, we got, if we do some substitutions on the previous side, and then we got the error term here, and then this is, and then you need to do some substitution here because the step size is just h, and then so we have h squared here. x0 minus x1 is h, and then this one is also h. So we got h squared here. So this is the error in the approximation by using the center difference formula. Does it make sense? So here we just use Newton's formulas, and I know some of you haven't taken the 104A because you are from another university. So I just go over the Newton's forms for like 10 minutes. So here we have the center difference formula. Any questions before we move on? So similar to what we have here. So we have, I just erase this, but before this, we have the cancellation error in the subtractions, right? And then the cancellations of the subtractions happens in the round off of the x and the round off for the y, right? And we have a similar things in the difference, the finite difference formulas. If we do the round off, for the formulas we have, so let's say we have, let's try this. So we have the H0. This is the center difference formula, right? We just derive this, and then we have 2H. This is the center difference formula. We use the 0 to represent. This is the center difference formula. This is formula, but if you are doing some round off, or in the computer it's doing some round off for this times and this times, let us assume that the computer only would do some round off for these 2 times, and then it would keep the exact value for this divisions here. And then let us investigate the errors in this round off. If we have some round off in the numerators, and then what would we get at the end? So let's say if up to some rounding off, and then for the denominator, for the numerator, we are using this time. So this is the errors in the fx0 plus h, and then this is the relative errors for this one, and then we are using this approximations value to represent this one in the computer instead. So and for this times we have another rounding approximations value for it, and because maybe due to the limited of the digits we have in the computer, and then we are doing some rounding off, and then we have the approximations relative error here is the delta negative, because this plus, because we have the plus here, and then this minus sign, and then I use the subscript here to represent this is the error term for the fx0 minus h. And now we are still using the 2h, and then we assume that we have the exact floating number representations for the h here, and then we do the exact calculations in the computer, and then let us investigate if we using these numbers to approximate these numbers, and then what's the error. So let's analyze this round of error here. So I'm just copy them all the things. So this is the approximations in the computer, and I'm going to copy and paste here. And this is the approximations value we are using. And then so for the true value we have, so let's just focus on this coefficient first. This is the one times this times, 1 times this times, and then we got fx0h minus fx0 minus h, and then divided by 2h. And then let us focus on what we have in the error term, and then in the error terms we have plus fx0 plus h, and then times the delta h. This is the error coming from the rounding off, for this time. And next we have another error part, and that is the error coming from the rounding off of the for the fx0 minus h. So this is the error term for this difference formula. So we are using the rounding here for these 2 values, and then so we are using some rounding for these two values so that we have such an error term in the difference formula. So this is the error term. And then now let me denote this as the, so this is the error term in the difference in the center difference formula. And this is the rounding off error. Oh, okay, you cannot see the color, so let me change the color here. Okay, this is the round of error term in the center difference formula. So, and I am going to denote this as the RH. And I'm using the RH to represent this rounding off because rounding off the first letter is R, so I'm using the R to represent it. And let's estimate this rounding off errors a little bit. So this RH is smaller than or equals to, we have two parts. The first part is the rounding off errors for the fx0 plus h. It's coming from this term. So let's just put the absolute values for the first term. And also we do the same things for the second term, and then we take the absolute values for the second term. And then we have such an inequality here, to term negative. So now one thing I need to mention is that, so here for the rounding off in the computer, and then the delta plus, and then the delta negative, it would be smaller than or equals to, it would be smaller than the epsilon. And then the epsilon here is the machine's precisions. So for example, if we have like 3 digits, 3 bytes, and then the if we have 3 bytes, and then the machine precisions, it should be like 2 to the negative 3, and then this is the machine precisions. And then I also mentioned this for the double precisions last time, and then the double precisions we have 64 bytes, and then but we only have 52 bytes for the significant, and then so that the machine error, it should be 2 to the 52, and that is the machine precisions. If you forget this, and then you can go back to take a look at the textbook or the lecture notes. And so now we have the delta plus, and then the delta minus, that is the error terms. And then this one is the, there's one extra term here. This two is smaller than the machine error because this is some rounding off in the machine, and then it's smaller than the machine error, machine precisions. And then so next we have this two is smaller than or equals to the epsilon. This is the machine precisions. And the next we have smaller than or equals to this plus the fx0h. And I'm going to combine these two terms together because I'm already bounding these terms and this terms by the machine precisions. And then I'm going to combine these two terms, and these two terms 2h, and then times the epsilon. Epsilon is the machine precisions. And as you would find out, this terms we have here, this terms here, the fx0 plus h, and then plus this things fx0 minus h divided by 2, is approximately, it could be approximated by the fx0. And then so we have, what we have left is the epsilon divided by h. So here, what have I done is that, so for a function, so let me just draw on here. So for functions f, right? And then let's say we have the x0 here, and then we have x0 plus h here, right? And then we have x0 minus h here. And let's say we have all positive value, and then we don't need to worry about the absolute value sign here. And then, so now, if we get a function of here, we get a function f. We get a function f. And then the fx, fx0h, and then fx0h plus h. And then this is the values we have here. And then if we put a straight line between them, we put a straight line between them and take the middle point. And what's this value? This value is exactly x0 minus h, and then plus the fx0 plus h, and then divided by 2. And so let's say we all have all positive value here, so that we can forget about the absolute value size a little bit at this moment. And then for this point, this is the average of this 2-point value. And then this value is here. And then we can use this point to approximate the fx0. And that's why we have such a thing here. And it is approximately the fx0. And then if we take the average of these 2 points, and then it's approximately this one. So now this is the error for the rounding off. It's approximately this rounding off error. Does it make sense? Each step. Okay. So this is not interesting at all, right? But let us do some very interesting. Let's combine. Don't forget that we have 2 parts. If you do the different center difference formula, so center difference formulas, we have 2 parts. So let's go back to what we have here. What are you going to do? Actually, it's doing this. Apply x0, and then so at very first, you want to approximate the derivative of the f, right? And then by the this is the center difference formula, right? But unfortunately, the computer doing some rounding off for you, and then at the end, actually you are using this to approximate your derivative. So one thing interesting is that you will find out that the results you get on the screen contains 2 parts of the error. Does it make sense? Because you are using this, the difference formula, to approximate this, but you cannot do the difference formulas in the computer because you have some rounding here, and then you use the rounding off formula to approximate that part. So we have 2 parts of the errors. For these approximations, you get, for these approximations, and then you would get the first part of the error. And then this part of the error is called that is class, what we have investigated in the last class, or just in the first 10 minutes in this class. And that is the errors in the finite difference error, difference formula. And then this is the first part of the error. And then the second part of the error is what we have just learned in a few minutes. That is the rounding off error. So if you want to do some calculations in the computer, it contains 2 parts of the error. So we have 2 parts of the error. So let's draw it analytically, and then to see what errors we have. And then this part is also boring. The next part is boring because it's analysis. But this part is very fun because you know now you know the error is containing it contains two parts. One is the finite difference formula, and then one is from the rounding off. So let us say this is the total error. I use the T to represent it. So once again, we are using the rounding off value to approximate to do the finite difference formula instead in the computer. And then now, if you want to analyze this error, one check is that at one turn and then minus another turn, minus the same turn. So what I'm going to do is to add one turn in between, and then that turn is the exact center difference formula divided by 2h. Okay, and I am going to add this back. So it doesn't change anything, right? And then now minus again, what I have here is the rounding formula. And then this is the another thing. And so what we have at the end, so now you can see minus sometimes and then at the same time, this does not change the result, but I can do this inequality here. It's more than or equals to taking the absolute value of here, the first term. The first term here we have, so this is the first term, and then this is the second term, and then I have it's bounded by the absolute value of the first term and the absolute value of the second term. So let me add one more page to explain the analysis here. So let's say, what is the first term? The first term is f prime x0 and then minus fx0 plus h minus f0 minus h and then divided by 2h. And this is what we call the errors in the error in the finite difference formula. And then where can we find this error? To remember what we have learned just in just like 10 minutes. So we can find out the error here is where we derive the center difference formula, and then we also get the errors here. The error is from here. Do you see it? It's this one. Okay, so we got the error, and then we have, and then let us do some things we all of us like, do some copy and paste. So this is the error term we have. And then what about the second term? The second term is here. The second term is the fx0 plus h and then minus fx0 minus h divided by 2h, and then minus the rounding things. The rounding things, 1 plus delta plus, and then because we have some rounding for the fx0 minus plus h. And then we have the rounding for this term as well. And then, so what about this term? How can we estimate this error? So this error, we have already analyzed it, and then let's go back to find it out. And then we have the rounding of error here. This is the rounding of error. So we are going to, this is exactly what we have here, rounding of error. And then, so I just say this is the rounding error, and then it is bounded by this thing. So let us just copy and paste these things to the next page. And this is still some boring analysis, but you will see some interesting results in a few minutes. So you have 2 tons, right? And then let us say, okay, now the total errors has 2 parts, and then because it's 0, h squared, and then plus the fx0. We have the absolute value here, epsilon x minus h. So maybe we can also take the absolute value here as well. So the total error is bounded by these things. So now you will see something very interesting. And if you, theoretically, if you are decreasing the step size, and then you will get more accurate approximations, right? But now considering the rounding off in the computer, you will have, so this is from the finite difference formula, and then this is from the rounding off error, right? And then now you will see, okay, this one is becoming smaller and smaller if I get the h smaller and smaller, right? But if you take a look at the rounding off error, we have some phenomenon similar to that cancellation error. If we get the h smaller, and then this error is actually becoming bigger, right? So what should we do if we want to get the minimized error? We should be smart in choosing the h step size, right? When these 2 terms are comparable, and you have already learned this in the calculus class. Do some minimizations for this function, and this function is about h. So let's say this is the gh function, and then so let us do this, and then this is a gh function, and then if you want to get the minimizations of this function, you would do this, and then you would do the critical point, right? So this equation, and then get the h value, and that's it. And then that would be your and also you can double check if the second derivative is the bigger than 0. You can double check this one. And if you solve this equation, and this gives us the h star, and then this is the critical point, and then it equals to fx0, and then epsilon, and then divided by the third derivative. And then I'm going to take the maximums of the function. And this one, it means that I'm going to taking the third derivative's maximums on the interval AB. And this now means the maximums of this value on the interval AB. And so this is the point, the critical point, and then I can substitute this point back to the GH function to get the minimum value. And you will see this at the end. This total error is with the magnitude. So this one is about the magnitude, is the machine precisions, and then but with the order 203. So now you can see that this is something interesting. So now what this one is not the machine precisions, because the machine precisions, it should be the epsilon, but here is smaller than the machines. This one is not the 1 order 1, and then we have the 2/3 order here. So we cannot get as precise as what we have in the machine precisions. Does it make sense? This finite distance formulas would have some chain off here, and then it would stealing some precisions away from your calculations, because we have some running off in the finite difference formula. What's the big 0 before the big 0 here is the order. It means that yeah, the order. So the order, it means that this is something we have mentioned in the math 104A, and then this is the big O, and then if you have H here, the step size, and then it means that it's equals to a constant times the H. but this constant would not change the magnitude here. And then it means that this is with the magnitude h. And then, for example, this h is the 0.1, and then this one, it should not change the h, the whole values here. And it only means the magnitude. Now, so how do you get this? How do I get this one? So I just substitute. So let us do some substitutions here. So I'm going to do the substitutions. I'm going to substitute this back to this formula. And then you will see this is just a constant, right? And then, but this one is going to the, so these all things, right, are constants, right? You can treat them as the constant, these things, right? We only care about the epsilon because the epsilon is the magnitude. So we have the epsilons 1/3 and then do the square. And then, so we have epsilons 2/3 here for the first time. Does it make sense? So we do the same things for the second time, and then this is just a constant, and then it would not change the magnitude. And then for this time, and then we just substitute the h into these things. And then we also give the constant value here because it will not change our magnitude, we suppose this. And then we have the epsilons and then divided by the epsilons 1/3. And then we have the epsilons 2/3. Does it make sense? So we have 2 times that is the epsilons 2/3. And then so it should be in the order of epsilon 2/3.
What is that notation in the denominator, the triple bar at?
You mean this one? And I just briefly mentioned, so I haven't written the formal definitions here. So let me clear all the notations here as well. So we have this. This is some things in the upper level of the mathematics course. It's the norm. And then this norm is just the maximum value x on the AB, and then for the F3WX. I just denote this as the maximum value. Questions?
So that's the absolute value of F3.
Yeah, absolute value, yeah.
Can you explain again why it's not machine position?
What?
Can you explain again why it's not machine position?
The machine position?
Yeah, why it's not machine position for result.
Because why it is not the machine positions, because the machine positions is the epsilon, and then the epsilon's 2/3 is not epsilon. So here the machine positions, it should be epsilon, right? And but here what we have is the epsilon's 2/3. And then what does it mean? It means that if you have for example, if we have the machine positions here, if we have the machine positions, for example, the machine position is 10 to the -3. If we have this for the machine positions, what does it mean by the total errors here? The total errors is in this magnitude, and then it's the 10 to the -3, and then 2/3. And then it means that we only have these precisions. This is the error. And then you will see this error is 1 order bigger than this one. And this is because we do some rounding off in the numerator before we processing further. Any other questions?
I have a question. So the fact that E of t converges at an error of machine precision to the 2/3, does that mean that the error that comes from the rounding is greater when H star is optimized? So when we choose, H star to minimize the error, right? And then the error, we found that it converges at an order of epsilon to 2/3.
Yes.
So does that tell us that the rounding error is greater than the error from the divided differences or the centered differences?
So this one is the total error.
Right.
Yes, and then is combining the finite difference error and then also combining the rounding off error. It's not greater or equals to, but this one is combining these two.
Okay.
Yeah.
Got it.
This is the total error. Because you need to do some trade-off here, you cannot just focus on the finite difference error because we have some rounding off errors from the machine.
Do we need to know how you calculate the edge star?
Wow, that's a good question. So we'll have a homework later on. And because these should be calculus questions, you are going to just get the formulas and then you just need to do the G prime H equals 0. Take the derivative and then let it to be 0 and then solve for the H. So I just skip the step here and then, but that's your homework.
Why is the denominator of H star instead of the derivative?
You mean why this one is
Why is it denominator of H star?
here? This one?
Why is it this instead of the?
Oh, because you are doing some, you can say, because why it is not the Casey-0, right? It could be the Casey-0, but you can, because the Casey-0 is between the A and B, right? And then you can use this value to approximate the maximum value to approximate this value. Do some approximation and maybe you can just like, but it would not change the magnitude. And then so we could do the maximums to get the minimizer. So maybe you would say, okay, this one is the F3, right? Because it's 0, and then that's true. This is the exact value. And then, but considering the Casey-0 could be anywhere, and then if you take the maximums of value, and then you could apply these situations to any situations. So I changed that to the maximum value.
Yeah, I guess that to minimize GH to BDH is different, depends on the points you choose.
Yeah, it would not, it would depend on the points you choose, right? Yes, it's correct. But if you take the maximums and it could apply to any situations. And that's why we choose that maximum value here to make it more general. But for this situation, you can just write it as this one.
Okay,
Yeah.
so
Good question. So maybe we can continue the discussions after class. We have more examples after this. So we have one examples here, and then that's how we choose. I'm showing you how to choose the optimal points with these concrete examples. So in the table here, we have, so we are going to approximate the apply, the derivative is at the 0.900. And then this is the value for the sine x here. And then if we approximate these values with the standard difference formula, and then we got such things. And we have choosing different exercise on the left-hand side here. And then this is the approximations value to the F derivative. And then we also calculate the errors on the right, the third column here. So as you see, I have different H step size here. And then the question is that how can we choose the optimal error, optimal step size H, right? And so let us take a look at the error we get. And then for this 0.1001, and then we get the error is 3P9. And then this one, if we choose a bigger step size, and then it decreases the error, 8.9. And then if we get bigger, the step size bigger, and then this is 5, and then we have 3.9, and you will see the error is decreasing, but after a point, after some points, and then this is 2 to the 5, and then this error is becoming bigger and bigger again, right? So it says that in the machine, it's not just decreasing the edge size to get optimal approximation, the best approximation. The best approximation is around this point. You will see it's changing from 1, 1, 1, 1, and then 2, 1, and then 3, 9. And then it could be the best approximations if you want to choose a step size. It's between the 0.005 and then it's between and the 0.05 here. So maybe it happens between these two values. And then let's double check. So by observing the table 4.5 here, and then we figure out that the optimal choice for the edge is happening between the 0.005 and then 0.05 because it's decreasing, and then after some point it's decreasing again, the error. And then so now from what we have previously, and then we have already analyzed the error, the total error for the center difference center difference formula, and then it is this way. And then the epsilon here, it represents, let me see, the m is just a constant, and then this is the epsilon. Epsilon is the machine's error, and then we have machine positions with the constant, and then m is a constant, and it's the maximum value of the third derivative. I just mentioned this, and this is what we have in the previous slides here. We have already analyzed these things, and so let's go back to what we have here. We just make it more simple. This notation is more simple. This is just we keep the epsilon and then we keep the m here, and then the optimal step size is the optimal choice of the step size is the cubic things here, and then that is what we have already analyzed here is the cubic things, cubic root of these things. And so we also have these examples here, and then at the end of the day, you would get the optimals. If you do some substitutions back to the here, the machine positions is this one. Because we have 5 decimal places in the f value, and then we have the round of error is bounded by these things, and then it should be the 6 decimals. And this is the machine's positions, and then if we substitute these things back to the h, this is the optimal choice here, and then by what we have analyzed before, and then we do some substitutions here, and then you will see the optimal choice of the h is around 0.0028. And this is a result consistent with what we have in the observations of the table 4.5. It's between the 0.005 and then to the 0.05. And then so we have the decreasing and then increasing error here. And then we guess it's between this interval. And then now we actually have this value, and this value is inside this interval. Does that make sense? Questions?
For m, why is x between 0.8 and 1?
This is this one, right?
Yeah.
Because you would see all the value we are using. So what is the biggest step size here, right? The biggest step size is the 0.01. And then what we are approximating is the 0.09. 0.9. And then so it means that if you add the do one step size forward and then backward, and then it should be the 0.8. And then one step size forward, it is the 1.0. And this is the biggest intervals we have. Good questions. Questions?
So, it seems to be different from our formula for GH, so there is, absolute value of X zero.
Yes, because we are, this one you can use the precise formula, but we are doing some, in this example, I just show you if we calculate it and then we got this. But
In this example, you do,
it would not change the magnitude, though.
you do know FX not. Right? So
Yeah,
that's
yeah,
why-
yeah, because the epsilon here, yes, I just ignore that fx0 there, but it would not change the result because the fx0 is just a constant.
But what if we were approximating a different function where FX not could be really large?
To be very large.
And in this sense, these two formulas would differ.
Okay, so if the fx0 is really large, then I think you might need to there you need to really do the exact formula. But here we just show some like not very rigorous examples here. And because the fx0 is not really large, it's approximately 1 here. It would not change the magnitude here. So I just skip it because it's easy to calculate. But if you're right, if the fx0 is really large, and then you cannot skip that fx0 here.
I mean, if it's really small, it also affects it.
Yeah, if it is very small or very large, it would still change the value. But here it's not the, we just want to keep the calculation simple when we are showing this example, right? But you're right, we need to use the rigorous formulas to get the precise values at the end. Any questions? Any other questions? Good questions. Yeah.
So if we were trying to apply this formula in an actual situation where we want it, it would be where we wouldn't have a exact, sort of formula for the first derivative, right? So then having a maximum for the third derivative would probably be quite difficult.
How would the maximums of the third derivative?
Meaning, how would we estimate the maximum of the third derivative? We can't even have a formula for the first.
Yes, that's a good question. So if we don't have the third derivatives, and that's true. And I think that would be, that's a good question. So I don't know how to answer at this moment. If we don't know, oh, I know. So a lot of time we don't get the theoretical error, and then we need to some other methods to so this one we have in the mathematics, in the numerical methods, we have two part of the error, and then one is called the priori estimates, and then this is priori estimate. It's before what we know. We don't know the f function, and then we just have this format, and then we don't know what is the maximum of the f3, and then but we still have the formula there, and then we have another estimate error, that is the posterior error. That is after something, after doing the calculation, and then you can estimate the error, and then you are actually using the computations result to estimate the error. So you're right, we have two kinds of error in the numerical methods. I think we have one more question, right?
I was just gonna say that if we regard the third derivative as a constant, the function is convex, I think. So you can like in practice, you could like sample points and find it.
Yeah.
Like is that the reason that would take the maximum?
Because we don't know where is the C0, so we are taking the maximum to estimate that one. Yeah, because Yeah.
It's just a common function. So
Yeah.
you can find it.
yes. So I think we have a lot of questions here, and then this is we have only 3 minutes left, but let us just take a look what we have the next class. So the next class is about the Richardson's extrapolations, and then this one is one add-on to the finite difference formulas, and then as you know, we have already investigated 3 formulas. One is the forward difference formula, one is the backward difference formula, and then they are of just first order precisions. And then so we have here. So we have for the forward and backwards approximations, and then we have one first order approximation, and then for the center difference formula, we have second order approximation, which means that we have the precisions is h to the order of 2, and then for the forward and then backward, we have only first order, and then the next class we want to get a fourth order approximation, and then by using some point value. And then that's the next class material. And then we are using the Taylor expansions next class. So if you forget what is Taylor expansions, go to do some review before the next class. And so that's it. And if you have further questions, you can come here. Wow, 准备太多了，救命！救命！你们不要不猜拳吧，小子。
就是因为是第4题和第6题没有考试，就我们还知道哪一题需要谁填哪一题。说只有第6题啊，
只有第6题需要抽证的，这一题它都是那种你用计算器就算一下就
哦，
行了。
计算器把数学。
对。
然后其实第4题我不知道这个 lost 就是 lost digits 就是对，其实我也不是很确定。我到最后我就是写了用。
我应该把这个就 Taylor expansion 就行。但是我这里的话，它 loss in double precision 就是因为 dt 这个是2的负5/2嘛，对不对？但是大概
16倍10。
其实我应该在这个作业上面提醒一下，这是什么意思？因为这个意思就是说，你们有时候去看到 error 的时候，他们会有一些有效数字嘛，对不对？对。然后，但是你如果在那里的话，你可能会发现有些到头来那个有效数字就变少了。对，就是那个 digits 是有效数字的意思。
但是就是如果玩计算器玩3x，它可能比如说8位，然后呢，但是如果我就只是单纯算的话，它也是8位。
这个
就是我用 Taylor expansion 就是差不多的
想想，你就把那个不是你用计算器的时候，你把那个精度调高一点，就是把它弄到10几20位，让你看得出来哪些 digits 是 lost 的，就是后面全都打成 zero 了。那不就是已经 lost 嘛？如果我们本来有1、5、3、4有5个有效数字，然后你后面看到，哎，你的有效数字只剩下2个，你就把那 precision 调高，就 Excel 里面。
但是就是我3x，比如说弄出来是个8位，然后呢，那我就是说如果它变成6位的话，那是 lost 2个 digits。
对。
但是我104，那我就还要再调高一点，因为我现在这是3x，我是104，
你调到20，你剩下它也会少了。
我也是，我就批的。对，然后我的这个 B 文是说怎么样解决这个 problem， 是我要讲 example， 就比如说我举例，我带个数进去，还是说是我就说因为它是个加法，它没有像减法一样。对，你就这样子解释就行了，就很像课上一样，就说你都没有那个，就是 没有像减法那个 operation。
相减，对，没有相减的那种会 modify 那个 error 的就行了。
我有问题，就是我感觉我这边一块儿有点没听明白，就是还有我第一个问题，就是 它的这个 delta 跟 epsilon 之间的关系是，就他们，因为我看你 notes 写他们都是 relative error，
对，
然后所以
epsilon 其实
我的
是
理解是，就是它这个代表它正的那个 relative error，然后这是负的，然后所以它上面这边不是说它两个加起来就是等于 epsilon，所以是这个加上这个就等于那个 epsilon，是这样子的意思吗？
不是，
啊
是这样子的，delta 的加还有 delta 减，它意思是因为我是用的这 subscript represent 这个，因为这里是这个 term 嘛，有个加号，对不对？是 for x0 plus h 的，这是 x0 minus h 的，这是这一部分的 relative error， 这是这一部分的 relative error， 因为我们做了一些 approximation for these two terms 嘛，对吧？对吧？这两个做了一些 approximation， 所以我们才有 relative error。所以用 subscript 来去代表这个的 relative error， 我用这个 subscript minus 去代表这个 error。然后
那最后那 epsilon
是那个 machine error， 就是machine precision not error machine precision， 这就是我们就把这个归，就是都统一定义、统一 notation 的。这个 epsilon 就是那 machine precision，machine precision 就是那个你计算机的精度能到达哪里，因为它精度不能到达，它就会做 rounding off。对吧
OK，
就是你像我们只有5位的计算机，然后它就不能做6位的计算，所以它有些 rounding off。然后那个 epsilon 就是说你的计算机精度能到达多精确。然后很像我上次说的 double precision， 我们就有那个精度是2 to -52 的那个精度，这样子。
那就像这边它不是写了2个，一个是 round off error，一个是
truncation error，
那就是它这个是怎么来的呀？因为我104A 学的有点烂，就是我上学期没学好。那个人
这个
讲
不光是这个是我们上节课讲过的，这个是 finite difference formula 的那个 error 来的嘛，对吧？这个是 finite difference 的那个 formula， 对吧？这个是我们想用这个 finite difference formula 去 approximate 这件事，对不对 ？approximate 这个derivative， 对吧？然后我们上节课的话上节课不在这儿，对。上节课的话，就是我们是做过这件事的这个是我们的总体的那个 idea 是怎么去 approximate 这个 derivative， 是用104A 的 knowledge 去 approximate。首先我们有个 approximation for the function f，right？然后我们就去 take derivative of this approximation。就是本来这是 approximation 的 Pn。然后但是我们如果去取它的导数，然后就去 approximate 这个东西的导数，对吧？这是 idea。所以这里的话，如果你要去 get 这个，因为我们现在就是做这个 approximation 嘛，我们用这个 approximate 这个，然后这一部分就是它的 error 了。如果我们也 take derivative of this term，
那这个它属于什么 error？
这个就是它的。所以我们是用这个公式去接近这个东西，对不对？所以这个公式就是那个 formula， 我们用的 formula 的 error， 对吧
？OK，
所以就是我们那个 class note 这次的，所以这一部分的话就是我们在之前 notes 有的，所以这一部分就是如果我们用这个 center difference formula， 然后我们就有这个 formula 的error。然后这一部分呢，就是我们 round off error。round off error 是因为我们用了一些计算机已经去接近了这两个数字，因为计算机它没有那么多精度，它可能就会做一些 rounding off。然后这一部分的 error 就是可以帮你 by this one。
OK，
是因为它要做一些估计嘛，它就 rounding up rounding down， 所以就有这部分的 error 在这里。但是这部分的 error 都是帮 by this one 的。
OK， 我知道，我来看一下前面细节，因为我一开始不在这个课，所以我可能前面有1-2节有些没听到。
没关系，就是如果没有，就是